Right now, a single ceramic pellet the size of your fingertip produces the exact same energy as an entire ton of coal.
There is no smoke, no open flame, and zero carbon emissions escaping into the sky.
Yet most people still picture glowing green barrels, toxic wastelands, or catastrophic meltdowns waiting to happen.
That misconception hides the vital engineering backbone keeping millions of American homes powered right now.
Inside the core, trillions of uranium atoms split apart underwater under extreme 2,200-pound pressure. This controlled reaction pumps thousands of megawatts directly into the Continental grid at exactly 60 Hertz.
If this system fails for even minutes, entire cities black out, hospitals stall, and transit lines freeze. So how do engineers safely tame atomic fission to continuously power 1 in every 5 American homes?
Let's cross the containment barrier and step inside the active core to see how it actually works. Every single second, the North American electrical grid balances millions of megawatts of instantaneous demand with absolute precision. Heavy manufacturing, digital infrastructure, and homes require an uninterrupted foundation of baseline energy that never sleeps.
Meeting this relentless 24/7 baseload without burning fossil fuels is the single greatest engineering challenge of our modern era.
Baseline is held by commercial nuclear power, the most energy-dense, reliable source of continuous zero-carbon electricity on Earth.
Let's run through the full generation cycle today.
Inside these reinforced fission, we're holding steady at 100% thermal power on Unit 1. Operating at over 90% capacity factor, a single plant runs continuously.
The towering plumes seen from miles away are entirely water vapor, releasing zero greenhouse gases, soot, or particulate pollution into the atmosphere.
This single ceramic pellet holds the energy equivalent of nearly 1 ton of coal, produced without releasing a single gram of carbon during fission.
Inside this hall, thermal energy released from atomic nuclei is converted into pure mechanical rotation on a massive scale.
Heavy forged steel shafts weighing hundreds of tons spin with microscopic tolerances, converting steam velocity.
Spinning inside a stator of thick copper coils, this single generator outputs over 24,000 volts at tens of thousands of amperes.
Transformers step this power up to hundreds of thousands of volts, minimizing resistance losses as electricity surges into the interstate grid. From this single node, energy branches out across hundreds of miles, feeding factories, water treatment facilities, data centers, and entire cities.
Critical services demand non-intermittent power. For life-saving infrastructure, continuous grid stability.
By supplying the unyielding zero-carbon bedrock, nuclear energy enables modern grids to integrate variable renewables without relying on fossil fuel peaker plants.
Reactor coolant temperature and pressure are stable on set point. Every thermal energy is monitored and regulated.
Everything we rely on out on the grid starts right here inside this vessel.
But how does a process occur?
To understand how this immense power is created, we have to look deep into the physics of the atom and the fundamental forces that hold matter together. At the center of nuclear power is a physical interaction that takes place on a scale 10,000 times smaller than an atom itself.
In 1938, physicists discovered that striking a heavy uranium nucleus with a single neutron could do something once thought impossible.
When an unstable heavy nucleus absorbs a stray thermal neutron, it deforms, elongates, and overcomes the strong nuclear force holding it together. The split releases 2 lighter daughter elements, along with 2 or 3 free, high-velocity neutrons traveling at thousands of miles per second.
The sum of the fragments is slightly less than the original mass. That missing fraction of mass becomes pure energy.
Because these heavy fragments cannot travel far inside the dense fuel pellet, their kinetic energy instantly converts into intense thermal heat through friction. However, the newly released neutrons are moving at over 10 million meters per second, far too fast to reliably trigger another fission reaction.
To slow a fast-moving object down efficiently, you have to hit something of nearly identical mass.
When exactly 1 neutron from each fission triggers another fission, the reactor reaches criticality.
The world's first artificial reactor proved the chain reaction was possible using raw graphite blocks and manual safety rods.
Under the direction of the United States Navy, reactor designs were refined into compact, robust, pressurized. Port established the American commercial standard: separate the high-pressure radioactive water entirely from the turbine. Shippingport proved that pressurized light...
Two primary light water reactor designs emerged across the American fleet: boiling water reactors and the more widely deployed pressurized water reactors.
This is inherent passive safety. If the water gets too hot, it expands, moderation drops, and the fission reaction naturally throttles itself down.
Commercial fuel is enriched to just 3 to 5% uranium-230 Fit5, physically incapable of producing an uncontrolled explosive yield. These ceramic pellets are stacked inside corrosion-resistant zirconium alloy tubes, bundled together into massive fuel assemblies.
Now that we understand the atomic and driving nuclear fission, we can examine the massive physical structures built.
A commercial nuclear power plant is divided to two distinct engineering zones: the nuclear island, heat, which...
Every building on this site is positioned to maximize thermal efficiency while maintaining strict physical and radiological isolation.
The containment dome is a fortress of engineering, constructed from 4-foot-thick pre-stressed concrete.
These steel tendons keep the entire concrete structure in permanent compression, ensuring the containment shell remains crack-free under extreme stresses.
Surrounding the reactor is the auxiliary building, which houses the primary coolant treatment systems, emergency pumps, and 4 independent safety circuits.
Adjacent to containment is the fuel handling building, designed for the secure delivery of fresh fuel assemblies and the long-term underwater management of used fuel. Massive insulated main steam lines carry millions of pounds of high-pressure steam per hour across this structural bridge directly into the turbine hall.
The turbine building is the mechanical powerhouse of the plant, engineered to house the heaviest rotating machinery on Earth.
High-voltage switchyards act as the plant's gatekeeper, automatically isolating faults and routing massive blocks of power onto the regional transmission grid.
Environmental protection starts right here. These traveling screens prevent aquatic life and debris from entering the plant's cooling systems.
Colossal pumps circulate massive volumes of water through the secondary condensers to cool and condense exhausted turbine steam.
Towers use the natural chimney effect. As warm water cascades down over internal baffles, cool air rushes upward, naturally shedding heat without large fans.
Plants use mechanical draft towers with motorized fans, offering a compact footprint while achieving the exact same thermal heat rejection.
Housed in dedicated tornado-proof structures, multi-megawatt emergency diesel generators stand ready to power essential cooling.
Every square foot of the nuclear island is safeguarded by multiple layers of automated physical security, hardened against all conceivable external threats.
Fukushima engineering added multiple external connection points across the site, allowing portable pumps and generators to supply cooling from any location.
Having surveyed the massive external perimeter, we now cross the physical barrier and step inside the armored containment shell to see where the core resides. Entering the containment building requires passing through a dual-door pressure airlock, engineered to maintain an airtight environmental boundary at all times.
The outer concrete provides structural strength against external impacts, while this inner steel liner guarantees absolute.
Directly surrounding the reactor is the primary biological shield, 8 feet of high-density concrete, engineered to...
This is the central pressure vessel, the most heavily engineered mechanical component in the entire facility. The reactor pressure vessel is the...
Constructed from massive seamless forgings of low-alloy steel up to 9 inches thick, the vessel has no vertical welds, eliminating structural weak points. The entire interior surface is clad in high-grade stainless steel, preventing the borated coolant water from corroding the heavy structural carbon steel underneath.
Dozens of colossal high-strength alloy studs clamp the upper head down, creating a leak-proof steel capable...
Penetrating the vessel head are the control rod drive housings, which use electromagnetic coils on the outside.
Inside the vessel, the core barrel directs incoming cool water downward along the outer walls, cooling the vessel's shell.
The lower core plate acts as the structural foundation for hundreds of tons of fuel, distributing millions of gallons of coolant evenly across every individual fuel channel. During refueling, the cavity above the reactor is flooded with borated water, creating a natural 23-foot radiation shield through which technicians can safely see and work.
Water is one of nature's radiation shields. Every foot of water cuts gamma radiation by more than half while keeping...
Leaving the reactor vessel, 30-inch stainless steel pipes carry 600-degree water under extreme pressure directly toward the steam generators. These snubbers allow the pipes to expand smoothly as they heat up, but lock rigid instantly if an earthquake hits. At the lowest level of containment, expansive passive strainer arrays ensure that emergency cooling water can be filtered and recirculated indefinitely without clogging.
Having unlocked the armored containment shell and pressure vessel, we now enter the active core to witness the nuclear fuel driving the chain reaction.
At the heart of the reactor vessel sits the active core, nearly 200 fuel assemblies containing over 8 million individual fuel pellets.
We don't use raw metallic uranium. These are ceramic pellets baked at over 3,000 degrees Fahrenheit.
Inside every fuel rod, hundreds of pellets are held tightly in place by a stainless steel spring and surrounded by pressurized helium gas for optimal heat transfer.
Zirconium is practically invisible to thermal neutrons. It contains the fuel physically without absorbing the neutrons needed.
To initiate fission in a brand new core, primary neutron sources emit a predictable stream of starter neutrons, kicking off the initial atomic cascade. As fast neutrons bounce off hydrogen protons in the coolant water, they shed their speed, reaching thermal equilibrium in less than a microsecond.
Slowing the neutrons down prevents them from being absorbed by uranium-238, ensuring they survive to split uranium-235.
When K effective equal exactly 1.0, the neutron population is perfectly stable.
Nuclear reactors are controllable because of delayed neutrons. Less than 1% of neutrons are...
To regulate power, neutron-absorbing control rods made of silver, indium, and cadmium are raised or lowered into the fuel assemblies with millimeter precision.
Control rods provide immediate local control, but dissolved boric acid gives us smooth, uniform power.
Burnable poisons like gadolinium are blended directly into select fuel pellets, naturally burning away over months. The brilliant blue glow is Cherenkov radiation, created when high-energy charged particles travel through water. Specialized spacer grids hold each rod with micrometer precision, using built-in mixing vanes to swirl the water and strip away heat with maximum efficiency.
Towards a slow wonder. Heat generated inside the ceramic pellet conducts across the helium gap and into the cladding, transferring millions of British...
Hundreds of internal thermocouples and neutron detectors continuously map the core in 3 dimensions, verifying that power generation remains balanced and uniform.
Even after all control rods are fully inserted and fission stops completely, radioactive decay of fission products continues.
With the atomic fission reaction fully controlled and generating immense thermal energy, we follow this superheated water into the steam generators to turn. To keep the 600-degree primary water from boiling inside the reactor, a dedicated pressurizer maintains a... Electric immersion heaters boil water to increase pressure, while cold water spray heads condense steam to lower it.
Superheated primary water enters the bottom channel head and is driven upward through thousands of microscopic heat exchanger tubes.
Heat transfers seamlessly across the thin alloy walls, boiling the secondary water on the outside into steam.
Cyclone separators and chevron dryers remove all liquid droplets, ensuring that only bone-dry steam leaves the steam.
Before reaching the turbines, the steam lines pass through rapid-acting main steam isolation valves, engineered to slam shut in seconds during an emergency.
The steam spinning these turbines is completely clean. The physical boundary inside the steam generator means radiation never enters the...
High-speed electrohydraulic governor valves throttle the immense steam flow, precisely regulating the turbine speed to match electrical grid requirements.
Steam enters the center of the high-pressure turbine, expanding outward through alternating rows of fixed and rotating blades to generate tremendous mechanical torque.
Before entering the low-pressure turbines, the steam is dried and superheated again inside moisture separator reheaters. 3 low-pressure turbines extract the remaining thermal energy, using massive titanium blades over 4 feet long to turn the main drive shaft. All 4 turbine sections are bolted into a single continuous steel shaft weighing over 200 tons, spinning smoothly at exactly 800 revolutions per minute. The generator rotor spins inside a sealed chamber of pressurized hydrogen gas, which dissipates intense electrical heat 7 times more efficiently than air.
As the massive magnetic field sweeps across stationary copper windings, it induces three-phase alternating.
Massive air-cooled aluminum bus ducts channel over 40,000 amperes of current directly through the building foundation toward the main transformers. Directly beneath the turbines, exhausted steam hits thousands of cold tubes inside the surface condenser, instantly collapsing.
These pumps develop over 20,000 horsepower each, forcing millions of purifier pounds of
Having witnessed how atomic heat is converted into mechanical rotation and immense electrical power, we now examine.
To keep the steam cycle operating efficiently, a third, completely separate water circuit continuously pulls. Maintaining an extreme vacuum inside the condenser allows steam to expand to its physical limit, extracting every possible megawatt of mechanical energy.
Before the condensed water is pumped back to the steam generators, it passes through deep bed demineralizers that purify the water to parts per billion standards.
We treat secondary water with precise oxygen scavengers and pH stabilizers to ensure these massive steam generator tubes.
Regenerative feedwater heaters use extreme steam to preheat incoming water, drastically reducing the
The auxiliary feedwater system provides dedicated backup cooling, utilizing diverse power sources, including a steam-driven turbine.
This turbine pump doesn't need external electricity. As long as there is steam in the generators, it can pump cooling water indefinitely.
Engineering diverse solid-state power controllers pulse electromagnetic coils in a precise mechanical sequence, raising or lowering control rods in 5/8-inch steps. Powered neutron detectors inside the core measure local fission density directly, continuously generating a 3D map of reactor power distribution.
Outside the vessel, X-core radiation detectors track neutron leakage across 9 orders of magnitude.
The reactor protection system uses 4 independent channels and 2 out of 4 voting logic, preventing false alarms while ensuring an immediate.
The system is designed to be completely fail-safe. If electrical power is lost, holding coils immediately drop.
Modernized nuclear plants utilize triple redundant distributed control networks, processing thousands of field sensor readings every.
Turbine governor in auto. Primary coolant average temperature matching reference temperature perfectly.
The control room interface is engineered around.
When grid demand changes, automated control algorithms adjust turbine steam flow and modulate control rod banks to balance.
Dedicated safety-grade DC battery banks ensure that all vital sensors, logic computers, and emergency valves.
Every sensor inside containment is environmentally qualified to survive extreme temperatures, high radiation, and subregions. With every supporting thermal loop, safety system, and digital controller operating in harmony, the plant is. Before connecting to the regional power grid, the generator's speed, phase angle, and voltage must match the grid with absolute precision. At the exact moment of synchronization, the generator breaker closes, locking the multi-ton turbine shaft into electric.
Once synchronized, the generator cannot speed up or slow down on its own. It is electromagnetically locked at exactly 800 revolutions per minute.
To increase electrical power output, the electro-hydraulic governor opens the steam valves wider, admitting more mass flow without changing shaft speed.
Commercial reactors are designed primarily for steady-state baseload operation, delivering maximum clean energy around the clock at peak efficiency.
Advanced software constantly calculates thermal margins across every single fuel rod, verifying that heat transfer rates remain far below physical safety limits.
Xenon 135 is the most powerful neutron absorber known. When power changes, operators must anticipate.
Scheduled load ramp, 20 megawatts per minute down to 80% rated thermal power. Modern light water reactors can perform flexible load following. Automated control systems continuously trim average coolant temperature, matching core heat generation to steam turbine power demand without operator intervention. Giant reactor coolant pumps drive hundreds of thousands of gallons of water per minute through the core, maintaining continuous forced convection across every fuel assembly. Advanced 3-element level controllers anticipate steam volume changes during load transitions, preventing water level instability inside the steam generators.
These feed valves modulate millions of pounds of water an hour with millimeter precision, keeping steam levels locked dead on target.
Continuous telemetry monitors thermal rejection to ensure the cooling loop operates at peak thermodynamic efficiency while fully complying with environmental regulations. Continuous vibration analytics track the balance of the multi-ton rotor train down to the micrometer, ensuring decades of smooth, uninterrupted rotation.
By adjusting generator excitation, we don't just supply megawatts of real power, we inject reactive power to support.
Dozens of continuous radiation and environmental sensors encircle the facility, streaming real-time baseline data to state and federal regulatory agencies.
Operating continuously for up to 2 years without refueling, nuclear power plants achieve an average capacity factor exceeding 90%.
Behind this flawless continuous power generation lies a comprehensive defense in-depth safety architecture.
Nuclear safety is built on defense in depth, 4 concentric physical barriers that isolate radioactive fission products from the outside environment.
During an emergency shutdown or SCRAM, electromagnetic holding coils de-energize, allowing gravity and drive. Pressurized nitrogen accumulators stand ready to flood the core instantly and passively if primary system pressure drops, requiring no pumps, electrical power, or operator action.
These pumps draw borated water from the massive storage tank outside, forcing coolant into the core against full.
A massive exterior storage tank holds hundreds of thousands of gallons of borated water, providing an immediate.
High-elevation spray systems condense steam and reduce internal pressure, while passive catalytic recombiners automatically eliminate hydrogen buildup.
Fuel assemblies are moved entirely underwater through an isolated transfer canal, using water as both a continuous coolant and a radiation shield. The spent fuel pool is a seismically hardened concrete basin lined with stainless steel, keeping used fuel submerged under 23 feet of continuously cooled water.
The fuel stays in this pool for 3 to 5 years. Water absorbs the decay heat and blocks over 9 to 9.9.
Spent fuel is loaded underwater into thick stainless steel multi-purpose canisters, lined with neutron-absorbing materials to ensure complete safety.
The canister lid is robotically welded shut, vacuum dried, and backfilled with inert helium gas.
The canister is placed inside a heavy concrete and steel overpack. Natural air convection cools the canister permanently without needing any moving parts or electrical power.
Stored on reinforced concrete pads, these passive dry storage casks safely contain all the used fuel produced over a plant's entire operating lifetime.
Because nuclear fuel is so dense, the entire lifetime electricity footprint of an average American produces used fuel that can easily fit inside a single soda can.
For permanent disposal, deep geological repositories enclose fuel in multiple natural and engineered barriers, safely returning materials to the Earth.
90% of the energy remains in use.
Advanced reactor technologies can recycle used fuel, turning today's waste into centuries of carbon-free energy.
With comprehensive safety systems and waste management engineering proven over decades.
The future of nuclear power begins on the factory floor, where small modular reactors are manufactured under strict assembly line.
By eliminating external pipes and large circulating pumps, advanced modular designs rely on natural gravity and convection for continuous passive core cooling.
Installing modular reactors underground provides natural physical shielding, seismic resilience, and an indefinite passive heat sink that cannot drain.
Goods pendant.
TRISO fuel cannot melt under any physical scenario. Each microscopic kernel acts as its own independent. Beyond electricity, high-temperature nuclear reactors can decarbonize heavy industries, producing clean hydrogen, synthetic aviation fuels, and heat for steel production. Repowering retired fossil fuel plants with nuclear reactors reuses existing electrical infrastructure and transmission lines while providing well-paying clean energy jobs.
Rotational inertia is the hidden anchor of the grid. These massive spinning rotors physically resist frequency drops, keeping
nuclear energy has the smallest land footprint and lowest material consumption of any clean energy source, producing immense power while preserving natural ecosystems. From remote polar communities to future bases on the Moon and Mars, compact nuclear reactors deliver reliable power where the sun rarely shines.
From mining and precision manufacturing to decades of generation and safe passive storage, every
single megawatt hour produced here replaces fossil fuel combustion, preventing tons of particulate matter and greenhouse gases from entering the air we breathe.
Winter blizzards, summer heat waves, fuel supply disruptions, none of it stops this machine. The fuel is already inside the core, ready to...
It is the ultimate synthesis of physics and engineering, splitting the atom to boil water.
From subatomic fission inside ceramic fuel pellets to thousands of megawatts surging onto the Continental grid, decades of engineering refinement have transformed atomic energy into the most reliable, power-dense, and safe baseload technology on Earth.
Day and
Night, nuclear energy quietly powers millions of lives, driving modern industry forward without producing a single puff of smoke.
And that is how nuclear energy works. Hengyu, from the ground up.
Clean, continuous, and immensely powerful. The atomic engine powering our world.